टेलीस्कोपिंग जो आप कहते हैं, टेलीस्कोपिंग कितने लेंथ के बाद टेलीस्कोपिंग में करना है? मैं अगर रिड्यूस करूँगा तो कितनी लेंथ के बाद रिड्यूस करूँगा?
क्वेश्चन बाकी जो ऑनलाइन है उनको भी समझ आए।
क्वेश्चन ये है कि टेलीस्कोपिंग जब हम करते हैं तो कितनी लेंथ के बाद मैंने पाइप का डाया रिड्यूस करना है?
While being the question is that if you want to do some telescoping, pipe telescoping, so what is the minimum or the maximum length that we can go for? Remember, there are two things to remember. Number one is how much a pipe can carry the fluid at the velocity of 1.5 meter per second. I'm limiting the velocity at 1.5 meter per second because I have a technical reason for it. I just want to minimize the water handling effect. We are not going into that detail, but as I need to minimize or to eliminate the water hammering effect, so I have to put a limit on the velocity that is 1.5 meter per second in irrigation system and in water supply system, right? Second parameter is the friction losses. And you have seen that ultimately friction losses account for total dynamic head, right? So there is no obvious minimum or maximum length before you can go for telescoping. It's all a hit and trial method. For example, I have a pump. Obviously, before that, for example, I want to design a particular system for a pump with a motor not exceeding 10 HP. So that is one limit mine. And I knew that with 10 HP, I can go up to 28,000 liters per hour, roughly, with a total dynamic head of around 45 to 50 meters. That I knew. If I exceed my total dynamic head to 55, I may need to switch to 12.5 or 15 HP. So my limit, upper limit, is 10 HP. I don't want to exceed 10 HP because in that case, I will enormously increase the operating cost of the system. That is one limit. Now, I will do telescoping for a particular size and will calculate the total dynamic head. And the total dynamic head, if it falls well within the 50 to 50 meters, I'm okay with it. If it is exceeding, then I have to do a telescoping in a way just to increase the 3-inch pipe to decrease 2, 1.5 and 1-inch pipe. Because in all that telescoping, what matter is the friction losses. For example, while designing the pump, designing the pipe, we learned that keeping the velocity 1.5 meter per second, we will have 28,000 liters per hour in 3-inch pipe. So it's a good design. But what if the pipe length is 1,000 meters? If the pipe length is 1,000 meters, let's be practical. Let's have a practical. Three-inch. Now, zoom. It's okay now?
Yes.
Okay. We have a 3-inch pipe. I'm answering your question, gentlemen. If it's 3-inch pipe, class B, the flow rate is 28,000 liters per hour, and the pipe length is only 50 meters. So head loss. Yeah, head loss is around 1.5 meter, 1.4 meter, around. It's very, very reasonable, right? But keeping the velocity same, keeping the flow rate same, but let me increase the pipeline to 1,000 meter. Now the friction loss is only that 1,000 meter is 27 meters, around 28 meters. And I knew the nozzle pressure which I have to give to that rain gun is 30 meters. So 27 plus 30 is 57, well above the 50. मैं एक example just आपको दे रहा हूँ. But now I have to include the suction head, the minor losses and all that. So it will well exceed the 60 meter head. Now what I will do, I will play around. I will go for 4-inch pipe. See what happens. With 4-inch pipe, the losses decreases to around 8 meters. Again, I would like to increase the flow rate, for example. It's again 21 meters. So you have to go for a hit and trial method, and we already have that Excel sheet for ourselves. And based on experience and based on that Excel sheet, we almost come to the conclusion within certain minutes or within certain seconds, quite a time, that what pipe size we have to select and how we have to do the telescoping. Now, what it has to do with the telescoping, for example, we have a flow rate of only 20,000. And we are going for 3-inch pipe. The flow, and we have to do the telescoping with 3, 2, and 1 inch, right? So with 3-inch, the flow rate, even with 20,000 liter, is around 14 or 15 meters. It's very high. Although it's well matching the criteria of velocity, and flow is well below the 28,000 liter per hour. It's 20,000. But the friction loss is so high that I have to eliminate 3-inch. I have to go for 4 inches initially. So 4 inch, note down 4.2, no, please note it down, 4.2 meter. After 1000 meter, the flow reduces to 10,000 liter. And the length remains the same. Now with 4 inch, it's 1.1 meter losses. Let's see what happened to 3 inch. It's 4, it's now very reasonable. So the next telescoping will occur after 1000 meter, right? So now it's 3, and then again 2, and so on. So this is not, I can't give you a specific answer that after this much of the meter, you have to go for another pipe. It's hit and try. You have to look to your available resources and then find it.
ओके थैंक यू। दूसरा सवाल ये है कि जिस तरह आपने बताया वाटर सप्लाई हमारे पास सिस्टम है, एक इरिगेशन का जो स्प्रिंकलर वाला सिस्टम है, जो स्प्रिंकलर सिस्टम है वो हमारे पास प्रेशराइज्ड होता है, तो दोनों में मटेरियल का नहीं बताया कि पाइप कौन से मटेरियल वाला यूज़ करेंगे।
दूसरा कौन सा बताया? एक
वाटर सप्लाई है, एक स्प्रिंकलर वाला जो
सिस्टम जब प्रेशराइज होते हैं तो इट लीस्ट मैटर कि वो जाके वाटर सप्लाई करेंगे या वो जाके स्प्रिंकलर चलाएंगे, इट लीस्ट मैटर। द टर्म प्रेशराइज इज इनफ, राइट? नाउ यू हैव टू सेलेक्ट द मटेरियल ऑफ द पाइप एज पर द प्रेशर ऑफ दैट सिस्टम, regardless what it is being operating. For example, in water supply, if you are providing to a whole city, if you are providing the water to whole city, you might need a higher pressure as compared to sprinklers. So in that case, you have by material, I suppose you want to say the standard.
Yes, material like GRP,
okay.
PPR.
From material point of view, let me say that these are 2 or 3 limitations. Number one is the cheapest thing is PVC. The cheapest thing is PVC. In PVC, we can have a pipe up to 15 bar, a pipe which can tolerate 15 bar pressure with different classes. We call that class A, class E, right? But if you are working in an area where excavation is not possible, or even if after excavation there are some rocks are there or any other foreign material which has sharp ends, then you can't go for PVC. Then you have to switch to some other category. And another material can be HDP. If you can't do the excavation, you have to go for HDP. PVC is out of the race now because PVC is not UV resistant. Ultraviolet resistant nahi hai PVC. So after some time, it will deteriorate. It will brittle or phad jayega, khatam ho jayega. So you have to go for polyethylene, I mean HDP, or for PPR, or for GI, or for MS. PVC is now out of the race. So you have to select either from, obviously in GI, then again the limitation is corrosion. In PPR, limitation is initial cost and the minimum external inner dia available for supply, because you must have seen PPR pipes, its wall thickness very high as compared to PVC or HDP. So normally in irrigation we don't go for the PPR. It's mainly designed for that green pipes. That green pipe are normally designed for household uses. So if I'm in place of you and if excavation is not possible, I will eliminate the PVC. I will, due to the UV resistance problem, and I will eliminate the GI due to corrosion problem. So what I'm left with is HDP. So that's how we have to go for it. But initially try to install PVC because it's cheap in price, but it must be buried. Remember, PVC must be buried. In hilly areas where this is not possible, so normally in earlier days we went for GI, but later on we have converted to HDP.
Okay, sir. We have one question from online audience. That is about the pipe telescopy. And what if we need variable outlet flow demand is in routine? So then the pipe will be telescoped or not telescoped?
Yes, we can telescope at that in that position as well. But I think what he would like, what he want to, what his question might be is that what about the friction losses, by the way? If flow is not constant, for example, as I mentioned in the presentation, that in first outlet it's 2 lph, second 2 lph, third 2 lph, and so on, then we can apply the F factor. But if in first outlet the flow is 2 lph, in second it's 10 lph, in third it's again 5 lph, then you can't apply the F factor. You have to go section wise. So if it was the question.
I think he said that then we can keep the same diameter all along the length if the outflow at different section is variable. So maybe at the last section, if the flow is maximum.
I will strongly recommend telescoping if the flow is variable. By the way, telescoping is by the for the varying flow. If the flow is remain the same, there is no need for telescoping. For your question.
सर एक और क्वेश्चन है माजरत के साथ सर जो 24/7 प्रेशराइज लाइंस होते हैं जिस तरह फायर सिस्टम के होते हैं तो उनके लिए कौन से मटेरियल यूज़ करते हैं
As I mentioned earlier, regardless what you are being using for it, you have to see the pressure rating of the pipe. For example, if the fire hydrant or the fire system pressure is 4 bar, for example, total dynamic is 4 bar, you can go for PVC class B. It will retain it.
We have 11 bar.
If you are 11 bar, you can go for PVC with class C, class B, sorry, 12 bar.
Thank you very much, Nasser Saab, for a very nice presentation and providing a very practical approach for designing piping systems and pump systems. I just want to know that ultimately the length of the pipe and the dia of the pipe is related to the cost. So do you have any comparative study in terms of the Hazzen equation and the Darcy equation? Because there are many reasons for which the Hazzen equation must not be used. It's controversial. It lacks some physical basis. It doesn't suit to laminar flow. It even doesn't include the effect of viscosity and temperature. So for that purposes, the Darcy is the better one. So do you have any comparative study? What would be the performance of the system based on the two equations and the cost of the system as well? Because ultimately you have to bear the cost. So if you get some wrong dia or length, it will cost you.
As I belong to irrigation industry or to water supply industry, where viscosity, where the fluid is water basically. So we are least concerned with the viscosity because the water viscosity, its specific gravity almost remain the same along the operating ranges that we are operating in the system. So I might not have that data. It might be available with the one we are dealing with within the industries. They are dealing with kerosene, honey, and sludges, etc. They might have that. But and also Hazzen William is a very good option for the turbulent flow. And most of the time in irrigation system we have turbulent flow, except the drip laterals, only the drip laterals, which maximum span, possible span practically is not higher than 100 meter. So within that 100 meter, we might have a difference of 1 or 1.5 meter at all. So it's least, what I must say that it's not remarkable difference. So I might not have that comparative study because my field of activity is entirely different, so only related to water.
Thank you.
Nasser Saab, it was a nice presentation, although I joined late. I have got a question. For example, I am supplying water from a point which is at a higher altitude to a point where the altitude is lower. Definitely it's through gravity. There is no pumping over here. But definitely the pipe will be pressurized, so it is ultimately a pressure flow. But my problem is that I have got a ridge in between these 2 points, and that ridge, the pipe will be passing above that ridge, and the highest point of the ridge is above the initial water level. So what could we do in this regard, whether to initiate the flow initially? Yes, that's
Something like
perfectly all right, yes. So what we can do to initiate the flow, because my perception is that if we initiate the flow once, then the flow, there will be flow throughout the time until we stop the flow. Thank you.
Let's assume it as a datum. That is the apex you are talking about.
Yes.
So if start point is higher than the end point, what we have to do is only to initiate the flow from this point up to that at once. Then we will have a siphon effect.
Yes.
But this point must be below that point. If it's, for example, if this point is somewhere here, below that point, but higher that point, then we have to install the pump.
No, the point is definitely lower than the initial point.
Then,
Yes.
like that. Then yes, we have to initiate the flow at once.
So how will you be initiating the flow?
For the first time,
Yes.
I don't have any idea about the pipe size or the length, but if it's a small, just as we do in agriculture, we want to take water from the water course to the field. Field is lower than the water course, but due to the ridge of the water course, what we do, we fill that small around 2 meter or 1.5 meter pipe. It's a siphon. We fill it with the water, with both ends closed. We place one end in the water course, another in the field. So it starts ultimately. But if it's obviously it is only for 2-inch or 3-inch pipe, which is possible. If this is a higher dia or the length is very high, then we have to install a pump over here. It will push the water to this apex, and once it's done, you have water over here, then you can discontinue them.
Okay, so the pump will be started initially, and after a certain time, like for example 2-3 minutes or 5 minutes, we can.
The moment you get a pressurized flow over here, the
Yes.
full mouth flow
Okay.
for this end point, you can shut off the pump. But if it's a full mouth flow, if it's not full mouth, it means that here this is not a pressurized system. Then, by the way,
Yes.
then it will become a gravity flow.
Yes.
The open channel flow. Then the siphon will not happen.
Okay, thank you.
I have a question, and it's mostly, it will be related to the system economics. डिस्कशन में हमने बात की कि वेलोसिटी हम 1.5 मीटर पर सेकंड इसलिए रखते हैं कि सिस्टम हमारा सेफ रहे और उसमें वाटर हैमरिंग जो है उसको करे, लेकिन हमारे जो इरिगेशन सिस्टम पर्टिकुलरली जो डिज़ाइन होते हैं और वाटर सप्लाई स्कीम्स वो डिज़ाइन होते हैं ओवर द स्पेन ऑफ 30 to 50 years, depending on if it is for agriculture, so to 30-35 years, और बाकी हमारे जो है up to 50 years लाइफ स्पेन के लिए. तो उसमें जो है मतलब आप हमें बता सकेंगे कि उस केस में चूंकि एक तो है सिस्टम की सेफ्टी, दूसरा है उसका जो कि फिक्स कॉस्ट के साथ उसकी डायरेक्ट रिलेशन बनती है, दूसरा उसका है सिस्टम की जो है टोटल इकोनॉमिक्स की जी, अगर हम उसमें इनिशियल कॉस्ट प्लस उसकी जो ऑपरेशनल कॉस्ट है उन दोनों को अगर हम कंसिडर कर रहे हैं, ज़ाहिर है वो फार्मर्स या किसी इदारे को पे करना पड़ रहा है. तो उस केस में जो है आपका जो है आपकी राय जो है क्या होगी कि हम किस तरह एक इकोनॉमिकल सिस्टम डिज़ाइन कर सकते हैं? क्या उसमें हमें ज़रूरी है कि हम 1.5 मीटर पर सेकंड की जो गाइडलाइन है वाटर हैमरिंग की उसी को कंसिडर करें, and it will give us a better economical design, या उसके beyond हमें जाना पड़ेगा?
For pipe design, there are, what I do is at least two parameters. Number one is velocity. Number second is economical pipe design. Number two is economical pipe design. That is another criteria how to design the system or do the piping network. But for a system, like you mentioned that for 40 or 50 years, so if I would have been the design, I will go for 1.5 or even lower than that. It's my option and my suggestion, because if I increase the velocity from 1.5, the flow will become fully turbulent, higher turbulent, the friction loss will increase, the total dynamic head will increase, ultimately the horsepower will increase. So if I'm running a pump or a motor of 50 horsepower for 50 years, that will be its running cost. And contrary to that, if I run a 40 horsepower or 30 horsepower motor for another 50 years, so that obviously over the span of 50 years, the 30 horsepower consumption will be far less than as compared to 50 horsepower. Although the initial cost might be little high due to higher pipe size. So if I would have been the design, I will go for even less than 1.5 meter per second. That's my suggestion. There is just no good design by the way.
Sir, I have a question about that. आपने जिस तरह कहा सर, हम ये वर्स्ट के सिनेरियो के बहुत ज़्यादा लेंथ पे पाइप डिज़ाइन करते हैं जिसका डिस्टेंस बहुत ज़्यादा हो सोर्स से लेके सिंक तक वाटर सप्लाई के लिए। लेकिन सर अगर इतना लंबा पाइप हम बनाएंगे तो हम उसमें कंसिडर करेंगे जो पानी हमारे साथ आ रहा है, जो आप लोग डिज़ाइन करते हैं एग्रीकल्चर सिस्टम के लिए रिवर से, तो सर उसमें इम्प्यूरिटीज़ और सेडिमेंट्स बहुत ज़्यादा होते हैं। तो सर उसकी कोएगुलेशन और जो सेटलमेंट होती है पाइप में, और हम वो उसके लिए अगर टेलीस्कोपिंग भी करें तो वो हमारे साथ बहुत ज़्यादा हो जाएगी सेडिमेंट्स, तो उसको आप कैसे डील करते हैं सर?
देखिए इन इरिगेशन सिस्टम नॉर्मली इन वाटर सप्लाई सिस्टम टेलीस्कोपिंग बहुत कम की जाती है। मेनली लूप होते हैं, वहां से फिर एक ही डाया के उमन घरों को या जो भी पार्क्स वगैरह को सप्लाई जाती है। इरिगेशन सिस्टम वी डू टेलीस्कोपिंग इन इरिगेशन सिस्टम, बट इन इरिगेशन सिस्टम वी हैव अ लॉट ऑफ फिल्टर्स at the head of the system. So we don't want the impurities to enter the piping network. And yes, if it entered, yes, obviously it will create a big trouble, not only due to the reduced cross-sectional area, also due to increased friction, because sand has a different friction factor as compared to PVC, but also prior to that condition, it will clog all the emitters. So it's totally unwanted phenomena. We have sand filter, we installed hydrocyclone filter, we installed disc filter if I talk about the irrigation system. So that is very important. And the telescoping normally occurs in sprinkler and drip irrigation, rather mainly in drip irrigation, in water supply or even in flooding system. The lift irrigation system, normally there is no telescope. Your question.